Hello, this is Matthias Kerschhaggl from EVK speaking. Welcome to our first digital talk and conference. Thanks for being here. Today I'm going to talk about quantitative chemical imaging in the industry. So, first of all, I'd like to introduce EVK, who we are. We are an expert company for industrial imaging, basically for the sensor-based sorting community. Our core expertise lies with stuff like hyperspectral imaging, as well as inductive imaging, metal detection, if you like. And we are providers of complete solutions, so we're not selling components or pieces of software suites. We like to bring the complete solution to our customers into the production line. So this is sort of a slide I like to show in order to get the idea across what we are doing and where EVK in this realm of sensors, software, data analysis and so forth is located. I would say we are located in the middle of the heart, in the intersection between what we call domain knowledge, so how does your application work, how does your production work, but of course we also do our own proprietary sensors because we are best at using them. We write our own software for data analysis and machine learning to harness the data we are actually producing ourselves. And this gives us the tool set to solve your applications. So one thing we really like to do, and what's for me personally is the most fun, is we bring laboratory-based metrology into the production line. So we make it fit for inline usage. So the motto would be, we bring the lab to your line. So what does that mean? For the most part, there are many applications out there where quality control is done using a reference laboratory, using high-end devices which are highly precise. But the problem is that for a product stream, these devices can only sample a subsample of the product, because you only can take a probe once in a while and then you get a very precise measurement. But if your product is very heterogeneous, the question arises if you can control the quality for the whole product stream accurately enough. So this is where we come into the game. We try to transfer the metrology from the lab onto our products to make the very same measurement fit for inline control. So this brings me to, I would say, a rather important differentiation between what we understand as accuracy and precision. So what's happening in the lab is you get a very precise measurement, meaning that if you repeat the measurement, it will stay more or less the same. But precision is not guaranteed to be the same as accuracy, because if you see this target here, you might be very precise in shooting, but still missing the target, which means in this case the target would be the true value of a quality parameter, your product features. And so more important than precision really is accuracy, meaning that you hit the target. In this other example, you see the same target with a lower precision gunman, but at least this gunman seems to hit the target closer, which for quality control would imply it's the preferred way to go. So in our case, what we are doing is we're trying to use the precision you used from the lab to make it also more accurate in the line, because we are, to stay in the same example, we are shooting more often. So you don't need a sniper rifle in order to hit a target with high sampling. It's better to use the shotgun. And what we are doing is we use the shotgun to really hit every detail of your product to bring the necessary data into your quality control. Okay, so to give you more examples from the industry, I try to get the idea across and talk a little bit about applications that are actually running out in the field or that are about to be introduced into an industrial environment. So this project involved the usage of household waste or refuse-derived fuels, and this waste contains all sorts of different waste products, from plastics, textiles, paper, wood, you name it. And this fuel is used for instance, in the cement industry to incinerate a kiln. The problem is the calorific value and parameters that are related to it, like moisture, there are as heterogeneous as the product itself. So if you take, let's say, a sample of such a square of refuse-derived fuel, you do not know if it's representative for the whole product. And accordingly, the temperature in the kiln might not be stable, and it's very difficult to control a process based on only on laboratory measurements, because there are too few measurements and the latency is too high. If I measure this value and I only learn the other day that it's not okay, it's not good for the production. So we tried to transfer this measurement onto our hyperspectral imaging camera using chemical imaging. As you can see here on this graph, you see different near-infrared spectra that come from our hyperspectral imaging camera, and they can be found in the material that is used for the incineration later. And you see there are so many different materials, it's really difficult to measure, let's say, the parameter like moisture for the whole product if you only measure a kilogram of this stuff. Of course, it's a real advantage if you measure the whole product stream all the time when it's fed to the kiln. So we used the measurements from the laboratory to train our camera system. Our camera has onboard classification capacities to use the hyperspectral data and to assign a measurement value to what the camera sees. And what you see here is a recovery function that shows the correlation between what the laboratory sees and what we see with our instrument. And the correlation, as you see, there's clearly a correlation there, is good enough to use this instrument in the cement production. So after having convinced ourselves and the customer that there is something to the story, we did also tests showing that the instrument really reacts swiftly to changes in the product stream. Here you see two images. On the left side, it's an image of the refuse-derived fuel as seen with the camera. This color, the color code you see on the very right side, depicts how moist the material is. So red would indicate high moisture, whereas blue pixels would indicate low moisture. And what we did is we artificially moistened the product by using some additional water. And in an instant, immediately, the camera showed more red pixels, as you can see on the right hand side of this image. So instantaneously, after 1 second, as the material arrives the camera inspection line, somebody, the operator, would notice that something changed, that the material is too moist, for instance, and that he or she has to react. So showing this with some numbers, we were able to transfer the measurement of humidity as well as gross calorific value or net calorific value onto our camera system with different accuracies. As you see here, the coefficient of determination as well as the root mean square of the calibration is shown. And these figures are good enough to already say, okay, this has some benefits to my production because it has the advantage compared to a laboratory that I get these values immediately with very low latency. I can create measurements every second if I like. Okay? So we tested this more thoroughly, and here you see two curves. The blue curve is what the laboratory said for the product stream, and the red curve is what our instrument saw. And there's one detail that immediately hits the eye. It's the variance of this curve is a lot lower if you use our Helios camera than if you follow the laboratory, for the simple fact that our camera sees the whole product stream and can average out local fluctuations in the product stream, whereas the laboratory only can sample, let's say, a kilogram of the material and thereby qualifies tons of material that are floating by in the same time by only 1 kilogram, which is not representative. And that's where these spikes are coming from. So you see spikes now and then, and they're not true. I mean, the measurement in the lab is true for sure, but they're not representative for the whole product stream. So if you put the material into the kiln is also doing an averaging because it burns all the material. And our camera can do the same averaging software-wise by counting together all the pixels, all the measurements, and you see overall the differences that are real and that the operator should take care of. The camera also sees, but local fluctuations are mitigated, and this is a big advantage. So we compared the measurements from the lab with our own measurements, and again we found this clear correlation, and therefore we made the application fit for the inline production. Now our customer can use this instrument for the same thing he did before, but the accuracy is a lot higher because he gets the information right away, doesn't have to wait for it, and can, for instance, control a fry unit further upstream in his production. I like to say that an image shows more than 1,000 words. So this image shows the distribution of moisture or dry substance, if you like, in a potato tuber. You can see it on the right, in the right image, where light is transmitted through a sliced potato slice, and you clearly see these water veins, right? But to actually measure that quantitatively, you cannot use a color camera. You have to use a hyperspectral imaging system in the near-infrared band like ours. And in the middle, you see this plot color-coded where the more red the pixels are, the more moisture you find in the product. So we convinced our customers and ourselves by comparing our measurements again with the laboratory. And what you can see on this plot is that if there are changes, real changes in the production, which we introduced again deliberately by changing the frying time in the production, then our instrument follows those trends. Whereas fluctuations that stem from the product, because one fry might be a little bit more moist than another, is averaged out. And so those local fluctuations, the laboratory is error prone to, we will not see and we will not need it. So we will not need them. So I would say this is a real step forward in quality control. And while we speak, these machines, as you can see them there, that comprise our Helios camera system, they're working in several factories at the moment. Another application I'd like to highlight is the measurement of the rancidity in walnuts. For this, our software use, CalLab5, was used, which enables the user to use the hyperspectral data from our camera and to assign measurement values from the laboratory to bring this application into the line. So on the left side you see the walnuts, and the ones that show more red pixels are obviously more rancid, whereas the ones that are more bluish belong to the good product. Such an application used for a sorter, like a sorting machine, was not possible beforehand because a color camera or X-ray or laser cannot really see the chemical composition, the chemicals. Our camera can do that, and our software has the data analysis tools to use that. Another application that we could solve is the so-called wooden breast defect. It's a defect you find in the poultry industry. It is, let's say it's a disease. It's not hazardous, but you don't want to eat it because if you see the chicken fillets and they're sort of hard and there's some liquid underneath the outer skin, it's just disgusting, and you certainly don't want to have that on your plate. So what the producers do at the moment, they use human personnel, trained personnel, well-trained personnel, I have to say, to sort such fillets out. But of course, as you can imagine, well-trained personnel is not easy to get, and the quality is volatile because humans might get tired and so forth. So we had the task to transfer what the humans are doing onto our system to automate the process. And I'd like to show you the next slide. So the goal was that we find out, and this is really domain knowledge, that we find out what the humans are doing, what features are they triggering at, and to transfer that onto the machine. So we were able, based on different parameters like hardness of the fillet or humidity and content of different molecules, to transfer what the human is doing here actually onto the camera. And you can see it here by defining a certain feature set using our machine learning tools. We were able to find features that sort of represent this defect. And you see on this plot the chicken fillets that are infected or affected, if you like, they show more pixels that show this feature than others. And as we speak, such a machine is working inline in a production line, and we are sure that there are more to come. And this is exactly showing the potential of our technology. You're able to transfer quality control that is done by humans or by high-end measurement systems in a lab into the production line where it's most needed. Okay, we did further tests, and the first tests were really promising. We had an accuracy of almost 95%, which for first trial was very good. But as I said, now we are already further. There's a machine out there working with even high accuracy. Another application would be the detection of poison in food, like here shown for bitter almonds. We also could solve this by using chemical imaging and our Scala tool. Here you see that, again, almonds that contain high levels of this poison show more pronounced reddish colors than the ones that are good. And this is also used on the sorter. So something you did in the laboratory before, and then you never had a chance to really qualify the whole product streams, because there are millions of almonds floating by. You only could pick out one and then say, okay, this is a bitter almond. But that was no real help for the real production. It was okay for quality control after production, but during production to sort them out, no way. Now this can be done. Along the same lines, we started with the identification of mycotoxins, for instance, in figs. This was a project, EU-funded project called My Toolbox. So also in this project, we were able to use chemical imaging and to detect the poison, in this case mycotoxins stemming from mold in the figs, and to sort out the figs that are not okay and that certainly are not fit for eating. One of our older projects from the pharmaceutical industry was the measurement of active pharmaceutical ingredients, in this case in a product that is used in surgery. It's a hemostat that should stop bleedings during surgery. And the thing is that the API here is a white powder, and if the concentration of this white powder on the sheet is not evenly distributed, it's not good for usage. But with a color camera or other, let's say, machine vision tools, you cannot really assess that. So hyperspectral imaging in the near-infrared regime is perfect for that, because we see the chemical composition. And as you can see on this slide, the concentration differences are nicely traced by the spectra. And we use that to help the customer here. And you see here the correlation between the measurement in the laboratory and our measurement is very, very good. This is also necessary for pharmaceutical applications. There, the accuracy has to be really high because of regulations like stemming from the FDA, for instance. And what you see on the next slide is that what appears to be only white to the naked eye really features different gradients in concentration distribution, which is really important to assess whether this product should go to a patient or not. So for our customer here, together we build a machine where our technology is used to really make the invisible visible and to show whether there are parts in the product that are not evenly covered with the API. And we did it, and this is working. So one of the newer applications we are about to to industrialize at the moment. It's ongoing work, is together with a customer of ours. It deals with the measurement of mineral oxides in the production line for refractory products. And here we compared our measurements to XRF measurements, so X-ray measurements, X-ray fluorescence to be precise. And we see that the correlation between laboratory-based measurement and what near-infrared can do for you are already pretty high. Of course, there are some differences you can see between the curves. We're working on that. It also shows the potential of our technology that obviously can be used also in the mining market. This brings me to the star of today's talk. It's our hyperspectral imaging camera, our new version, the Helius EQU32, which we designed for analytical tasks that I just showed to you. Because during our development, we have other hyperspectral imaging cameras. We used them predominantly for sorting. But when we started with analytics and quantitative analysis, we saw, okay, there are some features of the camera we have to improve to make the measurements even more precise. So we started to develop the EVK Helius EQU32 camera and introduce it for analytical applications because we use it for quantitative analysis. The thing is that this camera probably is the best camera on the market with respect to precision, throughput, optical quality for such applications, because we learned a lot during the last 10 years, I would say. And in conjunction with our data analysis algorithms, it really brings good results to the production lines, because we are now able to really harness the last bit of information you can find in such a near-infrared spectrum for quantitative analysis. I'd like to highlight that this camera features a superior signal over noise ratio, which you need for such applications, and that it also features pre-processing technologies in its onboard computing hardware that help a lot in bringing the information you need for your application into your data analysis software rather than noise or other unwanted signatures. So to say a little bit about our other products and about the EVK ecosystems, so as I said, apart from hyperspectral imaging, we also have metal sensors, so we call it conductivity imaging, because these bars, as you can see on the lower left side of this slide, they measure the inductivity or conductivity of a material that is floating by. So it's predominantly used for metal sorting, e-scrap, and so forth. And since we're out there for more than 30 years and know what to do with machine vision and know our business, we also offer color solutions. We were among the first companies to use color cameras for sorting applications already in the 90s. This is still our know-how, and we fuse the data of these different sensor heads together to make different sorting and monitoring applications possible. This is only possible because we have our real-time classification inference engine, which is integrated in the system, and of course our data analysis software to know what to do with the data all these different sensor types are producing. Okay, folks, thanks for bearing with me. It was a pleasure having you here. If there are any questions, you always can write me an email. I'm happy to answer. I hope you're well and healthy out there, and hopefully see you soon for our next digital conference here at EBK. Take care. Bye bye.